Hi. Today's lesson, P3, is about radicals and rational expressions. And we'll be talking about square roots and other roots, not just square roots, but roots in general. And fractions that have radicals in them. So we wanted to start out today with a definition of what it means to be a square root. M is a square root of n, so m is a square root of some number if and only if, folks, m times itself, or m squared, right, because we could write that as m squared equals n. Now there's a definition for square root, something that's oftentimes confusing to us, but if a number is a square root of a given number, then you multiply the first number by itself to get the given number. The difference between the term, the square root of n, and the symbolic radical n is that the term square roots can be positive or negative. So square root could be positive or negative. But if we're talking about the symbol means positive square root. So it means positive only. So we got to be careful as we're looking at problems to make sure if it's asking in words for the square root of a number, we could give the positive or negative square root. If this problem has the symbol in it, that means that we're talking about the positive root only. So with that background in mind, we're going to think about evaluating some square roots. And the square root of 81, you know and I know. The positive square root, because we're only talking about the symbol here, that's 9, because 9 times 9 is 81. So that's pretty straightforward. This one says give us the opposite of. See, when you see that negative sign out in front of an expression, it's good to think the opposite of. This says give us the opposite of the square root of 9. Well, the square root of 9 is 3, and the opposite of 3 is negative 3. Okay? On this one, we want the square root, positive square root of the quantity 36 plus 64. See, I had mentioned earlier in these videos that the square root symbol or the radical works as a grouping symbol. It does. Whatever work we can do inside here first, we have to do. So this is really asking us for the square root of 100. 36 plus 64 is 100. And folks, that's 10. I put these two here to illustrate a concept. No grouping here. This is a summation, or it's an addition of the square root of 36, which is 6, and the square root of 64, which is 8. 6 and 8 are 14. Two very different things here. Here we had to add under the grouping symbol. Here we had to simplify and then add, because that square root takes precedence over the addition. Here we've got the square root of a fraction, and some of you will remember from the other day that means we're talking about the square root of the top over the square root of the bottom, or 1 over 5 in this case. 1/5 is that square root. So some radical simplification. Next we're going to talk a little bit about multiplications and divisions with radicals. And folks, the product rule simply says this: if you have the square root of some product, m times n, that's exactly the same thing as taking the square root of m and multiplying by the square root of n. That is very different from what we saw on the previous page. On the previous page we were adding under the radical. Here we're multiplying, and if we've got something multiplied under a radical, we can break it out into its independent pieces. Very important when you start simplifying square roots. The quotient rule uses what we just used a moment ago with that 1/25. If we have the square root of a quotient, we can break it out as the square root of the top, the numerator, divided by the square root of the bottom, the denominator. We use those to help us simplify square roots, and I've got one here, and I'll show you the way that I teach this. I think to myself, if I want to simplify this, because I know if I put it in my calculator I don't get a nice round number. So if I want to simplify it, I have to break this thing up into its pieces, and I'm looking for pieces or factors of 75 that are perfect squares. So I want to check it to see if 4 goes into it, if 9 goes into it, if 16 goes into it, if 25 goes into it, because those are the perfect square factors, and geez, 25 goes into 75. 75, same thing as 25 times 3. Now, I want to do this because I can take the square root of 25. The square root of 25 is 5. And the way I show that is to cross it out here and bring it outside. And remember that whatever you bring out is multiplying the radical, right? This was all multiply to start with. So 5 on the outside, root 3 on the inside. There's the simplified square root of 75. This one uses the product rule in reverse. That is, if we've got these things that are being multiplied, we can multiply the stuff that's under the radical. 5x times 10x would be 50x squared. And now we can apply our simplification stuff. 50 is the same thing as, guess what, 25 times 2. So 25 times 2 times x squared. And we're going to take the square root of everything that we can. The square root of 25 is 5. The square root of x squared is x. So we're here, 5x comes out of the radical, and that root 2 is left under. Okay? Simplifying those radicals. Our next objective is involving adding and subtracting of square roots, and this is a little different, as is often the case. You can add or subtract like radicals, it's called. That is, they have to have exactly the same thing under the radical, like radicals. And as I'm looking at this does not look like radicals to me, but they're telling me to add or subtract. So either I can't do it, or there must be a way to break some of these further down. And in this problem, that's the truth. The square root of 12 is the same thing as the square root of 4 times 3. I'm going to just bring the rest of my problem down with me. I know the square root of 4 is 2, so that's coming out. Right? 2 is going to come outside this radical. So I'm going to have 7 roots of 3 plus 2 roots of 3. Folks, that's 9 roots of 3. And we wouldn't have known that unless we tried to simplify this radical. You can only add when you have exactly the same thing under the radical. All right, let's see if that will work here. Ugh. Looks like we're going to have to do a little bit more work, but we want to think about breaking down that 18 into numbers which, or factors, one of which is a perfect square, and I see that 9 goes into 18, so I'm going to go this route. 6 times the square root of 9 times 2 times x. All right, and I'll leave that for a second. Come back here. 8 is the same thing as 4 times 2 times x. And I'm thinking to myself right now, both of these are going to have a 2x left in them, because the square root of 9 is 3. That's coming out. The square root of 4 is 2. That's coming out. 6 times 3 is 18 times the root of 2x. And 4 times 2 is 8 times the root of 2x. These do have like radicals, so now we can do the arithmetic. 18 minus 8, do the arithmetic with the whole number parts. That is 10 times the square root of 2x, which was left inside. So you do the math with the whole number parts of these, the outside parts of these, as long as what's under the radical is exactly the same, root 3, root 3. Very good. So I know it's been a while since we talked about that. Probably Algebra 1, I'm thinking. Our next topic is important for us. We're going to use this all the time in trigonometry, rationalizing the denominator. You will remember that if you're talking about a radical expression, it's not okay to have a fraction, or to have a fraction where there's a radical in the denominator. That's not okay. The value of the numbers doesn't change, but what we're going to change is their appearance. And to rationalize a denominator, it's called, you do that by multiplying the top and bottom, the numerator and denominator of the fraction, by the smallest possible square root that would produce a perfect square in the bottom. Okay, that's just a lot of, you probably aren't going to ever remember those words, but that's okay with me. If I want to clear up this divide by root 3, the easiest way to do it is multiply top and bottom by the square root of 3. I want to have you stop here and think about this for just a minute. Algebraically, Any number divided by itself is 1. We are dividing by a convenient form of the number 1. That is what makes this an okay thing to do. As you think about this particular problem, I'm going to write it over here. 5 times the square root of 3 on top. On the bottom, root 3 times root 3, which is the square root of 9. Well, 9 is a perfect square. I can take its square root. The square root of 9 is 3. So my end result is going to be 5 times the square root of 3 all over 3. I've rationalized the denominator. And folks, we are going to use that often in trigonometry. This one, the square root of 8/12. I know for me, first thing I would do is split this out into 8/12 reduces. 4 goes into 8 twice, and I know that I can do radical over radical. 4 goes into 12 3 times. So I'm really talking about square root of 2 over the square root of 3 here. I rationalize the denominator, multiplying top and bottom by that convenient form of 1, which happens to be root 3 over root 3 again. On top in this one, root 2 times root 3. I can do it if it's a multiplication. That's root 6. On the bottom, root 3 times root 3 is root 9, which is 3. In fact, I probably will not continue to write that root 9 thing, because the whole idea here is you're multiplying by something that will get rid of a radical. And if I multiply the square root of 3 times the square root of 3, I get 3. This is simplified, folks. Don't let anybody fool you. You cannot divide this 3 into that 6, because that's not just a 6 up there. That's a square root of 6. Okay? So this is as simplified as it gets. Good reminder there. That was a good thing to put into this lesson. If we're trying to simplify a fraction, and we happen to have a sum or a difference, an addition or a subtraction in the denominator, you multiply, it says, by the conjugate of the denominator. Conjugate. Oh, the conjugate of a number, of a sum, okay, like this a plus b, is the same two number parts, a and b, but with a different sign in the middle. So if we want the conjugate of a plus b, we use a minus b. Okay? Let's apply that here. Okay, we're going to ask you to do a little bit of arithmetic here. You got to do a little bit of thinking. We've got a sum in the denominator of this fraction, and we got to multiply top and bottom then by the conjugate of that. It's going to be 4 same number parts, but with the different sign in the middle. 4 minus root 5. 4 minus root 5. On top, folks, no problem. This is 8 times 4, and it's 8 times that. So we're going to end up distributing and getting 32 minus 8 times the square root of 5. The bottom, though, that's going to take us something, because we've got quantity times quantity, and I know that some of you are going to remember this very well. When you're multiplying quantity times quantity, it's not just the outside you get, there are some guts there. 4 plus root 5. Remember the box method? 4 minus root 5. Oh yeah, I know you're remembering that. Quantity times quantity is when you use that box method. 4 times 4 is 16. 4 times root 5 is just that, 4 root 5. 4 times negative root 5 is just that, negative 4 root 5. And root 5 times negative root 5, well, that would be the square root of 25. Actually, it's a negative of the square root of 25. That'd be negative 5. Root 5 times root 5 is 5, and one of them was negative. Now, when you collect like terms, here's the beauty of this, and this is why we do it. The radical parts of this, 4 root 5 and negative 4 root 5, those cancel each other out, folks. They cancel each other. One's positive, one's negative. So we're just left with 16 minus 5, which is 11, right? 11 doesn't have any factors. There's no reducing that can be done. We've rationalized this denominator, and we did it by multiplying by the conjugate of what was on the bottom. I am going to ask you to take just a quick look at this, because I'll write the box method a few times, but I'm not probably going to keep doing that. When you see this conjugate business, the whole idea is you're getting rid of those radicals. It turns out being 4 times 4, that's the 16. Root 5 times root 5, that's where that minus 5 comes from. Okay, the guts drop out. And I'll probably show my box method for a while, but after a while I probably won't, and I know you won't either, because you'll see that shortcut. Let's go on. We've got one more thing to talk about here, and we want to talk just a little bit about higher roots and fractional roots. Okay, so higher powers than 2 and fractional powers of numbers. If we're looking at this, the nth root of a equals b, that means that if we raise b to the nth power, we would get a. The nth root of a is equal to b. That means that b raised to the nth power is a. If we're talking about, well, we'll take a look at some examples here in a minute. If n is an even number, if this is an even number, then the nth root of a to the n comes out as absolute value. You have to do that since you can't have a negative under the radical. So to avoid having a negative under the radical, when you take an nth root and n is even, you bring out the absolute value of. If n is odd, it doesn't matter. The nth root of a to the n will be a. Okay. As you think about that in these terms, you're taking the third root of 40. All right, I think I can deal with that. Now, instead of square roots, I'm cube roots. So the factors of 40 that are perfect cubes. 2 cubed is 8. 3 cubed is 3 times 3 times 3 is 27. 4 cubed, 4 times 4 is 16 times 4 is 64. These are some of the important cube roots, and of those values 8 is in 40. So we could rewrite that as being the cube root of 8 times 5. I think to myself, the cube root of 8 is 2. That's what comes outside. This simplifies to 2 times the cube root of 5. 2 times the cube root of 5. Alright, I get that. A little bit weird, just because I got to think about those, though. Fifth root of 8 times the fifth root of 8. Oh, my goodness. Okay, they're both fifth roots. So the product rule says I should be able to do then the fifth root of 64. And that means, oh my word, fifth roots. I'm thinking 2 is a good choice to look at here. 2 to the 4th is 16, 2 to the 5th is 32. And let's see, if we broke this up into 32 times 2, now you check me, is that the same thing as 64? And the fifth root of 32 is 2. So we bring a 2 to the outside, and we're talking the fifth root of 2 left inside. Okay, that looks a little bit weird, but you got to remember, we're never going to give you ones that you won't be able to figure out quickly like that. So think powers of 2, powers of 3. It would be very unusual for us to ask you to go the fifth power of 4. Most of us are just not going to be able to do that quickly. So we'll think about that. Our last one here, we've got a quotient, but you'll remember that we can take the cube root of the top over the cube root of the bottom. And again, whoops, again, we're going to probably be giving you numbers that are fairly easy to work with. The cube root of 125, y'all, that's 5, because 5 times 5 is 25 times 5 is 125. The cube root of 27 is 3, and that guy simplifies to 5/3. Okay, so higher roots, the properties remain the same. It's just that you got to remember you're working with a higher index, it's called here. Fractional exponents, this is definitely an Algebra 2 topic. You'll have seen this in Algebra 2. This says if the nth root of a gives a real number and n is an integer greater than 2, then these things are true. The nth root of a is the same thing as a raised to the 1 over nth power. That rational exponent has the same meaning as the nth root of. Likewise, if we're looking, comes out to be reciprocal, so 1 over a to the 1 over n power. All right, let's see if we can work that here. We've got a few examples to look at. Like this one, 25th to the 1/2 power. I'm going to remember this. The 1/2, that means we're talking about an index of 2 or the square root of 25. 1/2 square root 2. Let's see. That would be 5. Got that one. Negative 81. Oh, wait now. Opposite of the 1/4 power of 81. Okay, let's see if we can figure this out. Opposite of, and then it's going to be the 4th root of 81. Well, I'm betting, okay, I know that this one isn't a power of 2 because it's not even. However, I think it's a power of 3. 3 times 3 is 9. 9 times 3 is 27. And 27 times 3 is 81. So this is going to end up being the 4th root of 81 is 3. Opposite of 3 is an answer for this one. And notice that that exponent only applied to the number 81, not to the negative sign out in front of it. If we had wanted it to include the negative sign, we'd put parentheses. That's not what we wanted. Okay? 27 to the 4/3 power. Now that just looks funky, folks. However, there is a way to remember what to do here. The 3 is the index. So I'm going to write this thing as the cube root of 27. And you might think of it in 2 different ways. This is my favorite way, to the 4th power. Someone else might look at this and write it the cube root of 27 to the 4th, all under the exponent. Those things mean the same thing. To me, this is the easier representation because the cube root of 27 is 3, and 3 to the 4th power is 81. It's 3 times 3 times 3 times 3. Okay. That's my favorite representation. The index is the number on the bottom. The number on top, the numerator, that's the power of it that you need. If you apply that same thing here, we're talking about the square root of 4 raised to the 3rd power. That's 2 to the 3rd, and 2 to the 3rd is 8. 2 times 2 times 2. This one, I'm going to write up here because I'm going to run out of room, but we've got number stuff that we can work with and variable stuff that we can work with. So 20 divided by 5 is 4. And if you think about, if I write 4 as a number of halves, I get 8 halves. See if you agree with me there. 4 is the same thing as 8 halves. Do you agree? All right. Then we subtract exponents. And 8 halves minus 3 halves are 5 halves. Oh, now this is starting to look like something I can work with. All right. It's x that's to the 5 halves power. So if we're going to write this in a simplified form, we could leave it just like this. If we wanted to use the radical, however, okay, and notice the numbers are separate. That exponents were not attached to the numbers here. They were only attached to the x. So 4 is just 4. If we're going to write this in the radical form, we would write 4 times the square root of x to the 5th. I happen to like this better. And I would assume that most of us would rather see it in exponent form than in radical form. It's up to you, however. Totally up to you. Another way to write that same number would have the same value. 4 times the square root of x, all raised to the 5th power. All 3 of these representations say the same thing. Okay? I know that's a little bit weird, and it's been a while since you looked at that. So our homework tomorrow, when we get into class tomorrow, the problems that we'll be solving in school will all involve working with and simplifying radical and exponential expressions. Thanks for your patience. We'll see you tomorrow.